Yes, go ahead.
Are you going to post the notes in like slideshow format so we can see them, or just in the video format?
I can do both. Right now, I've only done the videos. Would you prefer it to be the slides?
Maybe for study notes, yeah, that would be.
Okay. Yeah, I can post them as a.
One though, or maybe
I can post them as a PDF. That's fine. Okay. Yep. Okay, so let's get started. So last week, remember, we talked about how atoms come together to form crystals and the different geometric configurations of crystals and how they affect the different properties. Very briefly, we talked about that. So today we need to understand in a bit more detail. So our goal, just to, before I jump into this, is to really understand how electrons behave in semiconductors and metals and insulators, because all of these together form the solid-state electronic devices. So in order to understand that, we need to understand the behavior of electrons in the simplest form of matter, which is a single atom. Okay, and from there we will increase the complexity. We'll put more and more atoms together, see how electrons behave. Now, in order to do this, we need to know some basic quantum mechanics, which you might have seen in your high school physics, but we're going to be very, obviously, applied quantum mechanics is a course in itself, like I mentioned last time, but here we will just touch the surface and point the very, very basic stuff. Okay? With that in mind, let's jump in. So the goal is to understand the basic mechanisms that determine electronic properties in crystals. That's the overarching goal of why we are studying this. Okay. First, we start with a qualitative understanding of quantum mechanics. Now, quantum mechanics started around 1900 or so because there were experimental observations which could not be explained by physics, the known laws of physics at that time. The most important ones had to do with two observations. One was the nature of black body radiation, and the second was the nature of the atomic spectra. Okay, we'll come to that in a second. So first, let's look at the black body radiation. So a black body is just that. Okay, it's something which is hot. The sun is a black body. Well, it is a theoretical representation of a real thing. The black body is not real. It's a mathematical construct, but it's something like that. Okay, you heat something up. Our bodies are also black, can be approximated as a black body. Anything that's above 0 Kelvin. Okay? And of course, anything that's hot emits energy, right? Because you feel the heat. You feel the heat from the sun. And this energy is emitted typically as light, right? Or photons, as we know it. At that time, people knew them as photons. Actually, at Newton's time, people thought of light as photons. But at this time, the theory was revised in consideration of wave theory by Maxwell and so on, with understanding that light is formed of waves. And we'll come to that also in a second. So at this time, when people were looking at this, they thought of light, whatever was coming out from here, as waves. Okay? But when they measured the energy as a function of wavelength, okay, they measured the spectrum, the color of the light, basically, right? So they saw that hotter things looked whiter, colder things looked bluer, right? And they had this certain distribution. And we know this now because if you look at stars, you can see it. The cooler stars are bluer, hotter stars are redder, okay? As long as they're in the same distance. Anyway, it's more complicated than that, but in any case. So it could not be explained by the wave theory of light. And you have to go through the mathematics to understand that, but it could not be explained. So we needed a new way of understanding reality. That's where this whole concept of quantum mechanics came about. Okay? So essentially what they observed was, Max Planck observed that a heated body emits energy in discrete bundles, which he called quanta. So he looked at the spectra, and the only way he could explain what he saw in terms of these colors was if he made the assumption that the energy coming out was not a continuous distribution of waves. If it's a wave, it's a continuous wave, right? Like an ocean wave. It just keeps going. But what he saw, when he formulated the mathematics as discrete packets of energy, so these are like billiard balls coming out, each containing a discrete amount of energy instead of waves, he was able to explain what he saw. that was the first indication that something was going to change in our understanding of reality. Okay, and this is obviously a very qualitative expression. The second most important thing that happened, of course, Max Planck won the Nobel Prize for that. The second important phenomena that was noted was the photoelectric effect, which of course is very important for us now, right? Because for solar cells, this is the basis of all solar cells. What was observed at that time was that when you illuminate certain kinds of materials, metals in particular, with photons, so you illuminate it with light, you saw that some electrons were kicked out. So you were able to observe charges coming out when you hit it with light. In addition to this, it was seen that if you look at the energy of the electron, the kinetic energy of the electrons that's coming out. Okay, electrons obviously at that time were thought of as particles, right, as we know, billiard balls. So if you look at the kinetic energy of the electrons as a function of the frequency of the input light. Okay, so if the frequency is a measure of the energy of the photon coming in. So if you increase the energy of the light going in, of course the energy of the electron coming out should increase, which kind of makes intuitive sense, but they saw a very strange relationship like that. It had a slope of h, which is the Planck's constant, and it had a little bit of an offset. And of course the wave theory of light was not able to explain this properly. So that was the second phenomenon. Okay? So Einstein actually looked at this and formulated the theory, which he won the Nobel Prize for, of explaining the photoelectric effect, assuming discrete bundles of photons. So his assumption was that if you assume there were discrete photons are discrete balls, let's say billiard balls, hitting the metal, it's imparting, the photon's imparting, so if you go back here, the photon here is imparting energy to the electrons in the metal, and if the electron gets sufficient energy to overcome the bonding forces within the crystal lattice of the metal, it can escape into vacuum with some energy, some excess energy. Okay? So and of course, intuitively now it makes sense, because what it says is that you need some minimum amount of energy here for the electron to escape. So if the frequency of light is below some threshold, no electrons escape. Okay? Which means that you need some minimum energy. And that was the bonding energy of the electrons within the metal lattice. That's what holds the electrons together within the lattice. And we'll come to that in the next chapter in a bit more detail. Okay? And he called that the work function of the metal. It's measured on this side, clearly. Okay? And equation for this, let me see. Okay, I gotta skip back a little bit. We'll come back to the equation in a second. So in the classical understanding of light was something like this, okay? It was an oscillation of the electric and magnetic fields, which I assume you have seen in your electromagnetics class before. So we have an electric field which is oscillating this way, you have a magnetic field which is oscillating this way, and they are counter-propagating. One generates the other generates the other, and so on and so forth. Okay, they're self-propagating waves. They carry energy. This was the understanding in 1900s. It's still correct today for most applications we're interested in. Okay, this is the Maxwell's theory of electromagnetics. Unfortunately, this is continuous. There's no discreteness here, right? This is the continuous wave. And, so some very brief background for those of you who might have forgotten what is wavelength and frequency. The electromagnetic spectrum spans a big range. You can have photons and the radio waves. So this is wavelength in meters. You have radio waves where you listen to radio and so on, with very large wavelengths, so it's about 1,000 meters, down to gamma rays, which is about 10 raised to minus 12 meters. Okay? Gamma rays come from stars and so on. Visible light is what we can see. Okay? By the way, the reason the visible light is what we can see is because that is the peak wavelength from the sun. And our eyes evolved to be very sensitive to that wavelength, which is about green. Okay. So you can see the wavelength is shown here. The frequency goes the opposite as the wavelength. So longer the wavelength, lower the frequency. Okay. And remember, the energy of a photon is h times the frequency, h being the Planck's constant. So as the frequency increases, energy increases. Okay, we'll review all this again, but just keep that in mind. So this was the picture at that time. There was no discreteness. Okay. But in order to explain this process, like I said, Einstein had to make this assumption that a photon is a particle of energy h nu, which comes in and essentially pushes an electron out of the middle with some energy. Okay? That's the whole idea. Now, this also raised the idea of, at this time, there were people who were doing experiments with diffraction. So there were some very unexpected results that were observed where even particles were shown to have wave-like behavior. We'll see some very brief examples later on. And it was postulated that all forms of matter at the atomic scale exist as both a particle and a wave. And this was referred to as the wave-particle duality. Of course, this is very non-intuitive, but this is the way nature works at the atomic scale. Okay? So essentially what it says is that all forms of matter and energy, electrons, photons, protons, etc., behave as particles and waves simultaneously. Okay? So it's obviously nothing to do with common sense. This is, in a sense, you can think about this as a mathematical construct that explains reality. Okay? And of course, there are revisions to this today in string theory and so on, which is still not fully resolved. Okay? But in any case, the idea is that if you have a wave which is traveling, it is always associated with a particle. Or the other way around, if you have a particle that's traveling, it's associated with a wave, whether it's an electron, photon, proton, whatever. Okay? Even anything is associated with the wave as well. And it's a wave function, as we will see in a few minutes. Okay? And in general, more complicated waves can be built up by a superposition of waves as shown here. Again, don't worry too much about the math at this stage. We'll come back to it. And the postulate was made by de Broglie as follows, that the wavelength of a particle is related to the momentum of the particle. So remember what's saying here is that if a particle is also a wave, so then the question arises, what does that wave look like? Now, how do what we generally consider the properties of a particle, how does that relate to a wave? Okay, so the general property of a particle is its momentum, its mass times its velocity, right? That's p, and the postulate was that lambda equals h over p, where h is a Planck's constant. So you can see for particles which are very big, massive, m is large, velocity is large, this lambda is very small. Okay? And if the other way around, if they're very small and moving very fast, the lambda is large. Okay? So anyway, keep this in mind as we keep going. The third phenomena that was observed in the early 1900s was the phenomena of atomic lines. Okay, so you've seen this in storefront signs and so on. Neon glows with a particular color. Right? It's a very sharp color. It's not like the sun, which is white. Okay, sun has a mixture of atoms. If you take a single kind of an element like neon and put it in a plasma and put high voltage across it, it'll glow and emit light at a particular color. Very, very sharp lines. Argon, a lot of atoms to it. All the atoms to it, in fact, right? So people measured these spectra in the early 1900s and saw that they had some very specific relationships between them. Okay, an atom can emit at different colors, but they're all very sharp colors. Okay, and there was some relationship between them. They were not able to explain that. That was the third phenomena that needed explanation. So emissions from atoms occur at specific wavelengths of frequencies unlike a black body. An example is for hydrogen, as shown here. The atomic lines of hydrogen are shown here. If you take a hydrogen atom and put it in a plasma and put a high voltage, you will see all these lines. You'll see very specific lines like this in the ultraviolet, blue, a little bit less blue, and all the way up to the red. So you'll see all these lines. And they're very discrete. And people noticed that there was a relationship between the wavelengths of these lines, a numerical relationship, and they were not able to understand why. There's no explanation of why they should behave this way, and all the atoms actually demonstrated this. So that was again another phenomena that needed explanation. Okay, the energy relationship which we just talked about is h nu, h times the frequency is the energy of a photon. Of course, frequency can also be written as omega divided by 2 pi, right? Frequency, omega is the radial frequency, Nu is the cycles per second. H bar is the representation of h divided by 2 pi, h being the Planck's constant. Again, you don't need to memorize all of this. You can look it up. So nu is, of course, related to the velocity of light and wavelength as nu equals c over lambda. These are the basic dispersion relationships. Okay? All of these you should know. If you don't, go back and review. I won't go through it too carefully. Okay. So the explanation for those discrete lines that we see in the hydrogen spectrum was given empirically by scientists as follows. They made the assumption that if you assume that the hydrogen atom can exist in very discrete energy levels, as shown here, n equals 1, 2, 3, 4, 5. So instead of having a continuous distribution of energies that the atom can occupy, you only have very specific energies, only allowed energy states. If you make that assumption, then you can explain all the lines of hydrogen that we saw. So for instance, the reddest line of hydrogen comes from this transition, from n equals 2 to n equals 1. That is the lowest energy. So if a hydrogen atom relaxes from this higher energy state to a lower energy state, it can emit a photon of energy equal to the difference between the two energy states. Okay. Now clearly, if you're relaxing, if the hydrogen atom is relaxing from a higher energy state, the photon that is emitted has a higher energy, right? Because the difference in energy is higher. Okay? And you can have all kinds of relationships between the different levels as well. And this was able to explain what people saw. Okay? But they did not know why these atomic levels had to be discrete. That required quantum mechanics, but they were able to explain it based on this picture of reality. Okay? So at this stage, I know we have presented a lot of very abstract concepts. So I picked a very, simplistic video, which actually goes through some of these very, very simple things. And we can take a break and think about this while we watch. It's only a few minutes long. But it's kind of interesting because it, if I can get this, it addresses some of the key issues of quantum mechanics, which most of us find a little bit hard to comprehend. Oops. I got to go through that. This is a good break before we jump into all the math.
Object, say a marble, at the screen. We see a pattern
okay, I guess
on the back wall where they
I don't know if you can hear it.
And hit.
Can you hear
now, if we add a second slit, we would expect to see a second band duplicated to the right.
Those are particles, right?
Now,
that's a
let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands.
So this is the classical.
Good so far. Now,
what one expects.
Let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons. tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Okay. So it had a couple of interesting points. First was the... sorry. So first, you notice the wave-particle duality, right? So you see, they shoot electrons at it, and you still see the wave phenomena of diffraction. But the other part is what we're going to come to, which is the uncertainty principle, is that the fact that someone watched the electron changed the reality. Okay? And so this issue of observation and observables and what we can measure, what we cannot measure, turns out to be a very, very important point in quantum mechanics, and also in this class, as we will go on later.
And here we are, the granddaddy of all quantum weird.
Okay. Oops, I think I missed something. Hang on a second.
The infamous double slit experiment. To understand this experiment.
Let me make sure I didn't miss something. Okay, I did not, so that's good.
We first need to see how particles, or little...
Okay, now we're back to the model. So the idea then, of course, we had all these strange observations, so we needed some model to explain it. So Niels Bohr was the first to actually propose a model to explain the spectral lines of hydrogen. And of course, he won the Nobel Prize also. He's perhaps one of the most important physicists in this whole era, in addition to Schrodinger, which we'll see in a minute. Okay? So what Bohr was trying to do was trying to explain those spectral lines where we saw those energy differences giving rise to those colors in the spectral line. How do you explain that? How do you explain those the discreteness that you see? Okay? His first postulate was to use the planetary model to explain the behavior of electrons around a nucleus. So he assumed that an electron essentially orbited the nucleus. So in the case of hydrogen, we have one proton and one neutron, sometimes more than one, but then you have an electron. right? It just orbits around the nucleus at a certain stable radius. Now, in classical electromagnetics, this is problematic. This is not a stable system because the electron is a charged particle, and we know from Maxwell's theory, if a charged particle is accelerated, if it goes in a circle, it's accelerating, it needs to emit radiation. Okay, this comes from Maxwell's equations. Now, so Bohr had to make the postulate that there are stable orbits where no radiation is emitted. So electron can exist in stable orbits around this nucleus. Okay? And so those are the few assumptions that he had to make. Later on, people came back and explained all these assumptions. So he had to make these ad hoc to explain the spectral lines. First, the electron forms a stable circular orbit around the proton. The electron can occupy only discrete energy levels, as we will see. And that was explained later on by Schrodinger, but this was the postulate. And the angular momentum of the electron is quantized. Okay? And this has a very specific physical meaning. We'll see in a second. But the angular momentum defined as, remember, it's m, the mass times velocity of the electron times the radius of the orbit. That's the angular momentum. Again, we'll see that later on. It is quantized as follows. It can only have discrete quantities as nh over 2 pi or nh bar. Okay? H bar is h with a line through in the top, and it's also called the reduced Planck's constant. Okay? Now, this has a very specific meaning, which is, okay, first of all, the discrete energy levels essentially explain the discrete lines that I showed, we saw before. If your electrons can occupy only very discrete orbitals around the nucleus, then if the electron falls from one of the higher orbitals down to the lower orbital, it can emit a photon. Okay? And by picking the right radii of the orbitals, you can explain the spectral lines. Okay? We will calculate the orbitals shortly, so they are not arbitrarily picked. They can actually calculate this. And we can do this. That's not very hard. The second condition of the quantization of the angular momentum leads to this physical model. It is the same as having an integer number of wavelengths fit within the circumference of the electron orbit. What that means is that, remember, the electron is also a wave. So if it has a circular orbit, the assumption of the quantization of the angular momentum says that you have an integer number of wavelengths which fit within the circular orbit, as shown here. So in the case of n equals 3, you see an integer number of waves. 3 waves in this case, and 2 waves in this case, and 1 wave. These should be overlapped. Okay? And this is actually one of your review problems tomorrow, so you will actually solve it. Okay? Essentially, you can think of them as standing waves of matter set up around the nucleus of the hydrogen atom. This is the condition, n lambda equals 2 pi r. Okay. Now, how do we calculate the electron orbits? They are very straightforward, so we can all do this based on just high school physics. Okay? With some certain assumptions we have to make. The classical part is very straightforward. The electron is held in orbit by electrostatic attraction. So you have an electrostatic attraction between the proton and the electron, which keeps it in orbit. Okay? So you have a centripetal force, which is equal to the Coulombic force. The Coulombic force is just from electrostatics. It's just the atomic number, in this case of hydrogen, is 1. Ke is just a Coulomb constant, 1 over 4 pi epsilon naught in SI units, E squared over R squared. Okay, this just comes from electrostatics, very straightforward, right? Is equal to the centripetal force, again from your high school mechanics, right? It's mv squared over R. Okay, these are just the two forces, centripetal force and the electrostatic attraction. Remember, the centripetal force is trying to pull the electron out. So it's like if you take a string attached to a ball and put it swing it in a circle, it's trying to escape, right? So you can solve this equation and calculate the electron speed, the velocity from there. Just becomes square root of zke e squared over me r. Okay? The total energy of the electron also depends on the radius of its orbit. You can solve this. And the energy of the electron is just the kinetic energy. Right now, it's half mv squared. Okay? Minus zke squared over r. So sorry, this is the kinetic energy and this is the potential energy. Remember, the electrostatics comes from also potential energy. So you have to add the two energies together. Yes?
Sorry, I missed that. What is Z again?
Z is the atomic number. In hydrogen, it's 1. So you can just set it to 1. Okay, it's a number of protons, number of charges essentially. Okay, so the total energy can be written as the kinetic energy minus the potential energy. The potential energy is negative because you need to do work on it to remove them, right? If you have two charges which are attracted to each other, the energy of that system is negative because you need to do work to actually separate them. Okay, that's just a convention. And you can get a total negative energy. The negative energy means that the electron is in a stable orbit, which means if you want to remove the electron from the atom, you need to do work on it. That's what that means. Okay, so once you have that, so all of this is very straightforward. This just comes from basic high school physics, okay? Now we have to make some assumptions, okay, on the quantum part. The angular momentum is an integer number of the reduced Planck's constant, which we just saw. That was one of the postulates. So MEVR is NH bar, okay? We make that discreteness assumption. Then you can calculate the orbit Rn by going back to this equation. Okay, you can substitute MEVR by the quantum number NH bar, and if you put it in here, you will get an equation as follows. Okay, of course you have an index n because you have now discretized the radius. By discretizing the angular momentum, now you have discretized the radius of the electron around the orbit, around the nucleus. Okay, so now we have this expression which allows us to calculate where the electron is orbiting the nucleus. Or in other words, now we can calculate the size of the atom, because the hydrogen has only one electron, right? And it turns out to be, n equals 1 is the smallest size of the hydrogen atom. It turns out to be something like about half an angstrom, 0.6 angstroms or so. And that's called the Bohr radius. The energy of the electron, the nth energy level, of course, is what we are interested in because we are trying to explain the spectral lines, remember? So we need to know what the energy levels are so we can take the difference between them and then calculate what is the energy of the photon that came out. And that, of course, is fairly straightforward. Again, from the previous expression, from here, you can just plug in the expression for the R, and you get something like that. Again, it depends on n. And can be shown to be something like that, minus 13.6 over n squared electron volts, Z equals 1. Okay, now, once we have this, then we can go back and plug in the numbers and see if it actually explains the spectral lines. It turns out they do, which is why Bohr won the Nobel Prize. He was able to explain the observation based on this fairly straightforward model, okay, with some very important assumptions. So the atomic spectral lines can be explained. Essentially, if an electron goes from n equals 3 to n equals 1, it loses an energy delta E equals to h nu. And delta E is just E initial, the energy of the initial state minus the energy of the final state. Very straightforward. And it can also be written as the Rydberg constant, Re times 1 over. Remember, the energy goes as 1 over n squared, so you can just write it as 1 over nf squared minus 1 over ni squared. Remember, they are negative, so they get flipped. Anyway, you can plug it in. It's not that difficult. And if you, the Rydberg constant is just those materials absolute constants. They don't depend on anything. Okay. And the wavelength of the emitted photon is just 1 over lambda is r times that. Okay. Where r you have the h over c over lambda, right? Remember, energy is given by hc over lambda, and you can plug it in and get those equations. Now, this expression was, of course, able to explain this. So the wavelength here and these different lines could be explained by these transitions between the different orbitals. So that was the whole, I would say, to a big extent, the success of the Bohr model to explain reality. Now, this was a very simplistic model in the sense that the hydrogen atom is a very simple atom. There's only one electron, one proton. Very simple to model. But of course, most atoms have many more electrons, many more protons, and so on. It requires a much more complicated description. Okay, and we won't actually go into it. But in fact, there are no simple explanations. You cannot actually solve the equations. They're too complicated. But you can have approximations that explain reality. Okay? So till now, we have gone through I would say, very abstract, in a very abstract sense of what these things mean. And I went through them very fast. So I would suggest you should go back and think about them and do some of the review problems when you get a chance, which I will tell you what they are at the end of the class. Okay? But in the rest of the class, we need to actually do some of the math to understand how we can make use of these quantum concepts in the rest of the class to explain how electrons behave in crystals and so on. Okay, so far it had been qualitative. Now, however, now we need to actually do some math. Not too complicated, because we'll just make some assumptions, but relatively straightforward. So very basic quantum mechanics in 10 minutes. So we have to first start with understanding that in quantum mechanics, observable quantities like velocity, energy, time, position, all of these things cannot be observed with absolute precision. Okay? This is a very fundamental nature of reality, and it was the basic assumptions that one had to make. And this is based on, and this assumption is what's referred to as the Heisenberg's uncertainty principle. Okay, and we'll look at that in a second. But basically what this means is that if you, let's say we are interested in the behavior of an electron in a crystal, which is what we're trying to understand, if you want to understand the energy of the electron, there is no real way to know it extremely precisely. There is a limitation, how precisely you can know it. Or if you want to know where an electron is, there is a limitation on how precisely you can know it. Okay? Another way to think about it is that you can only know the probability of a particular value for the velocity of the electron, or a probability for finding an electron in a particular location. So in quantum mechanics, what we calculate is very different than what we do in classical mechanics. In classical mechanics, you say a truck has a mass of 10 tons, it moves at a velocity of, 10 meters per second. What is momentum? You can just multiply them together. That's the number. In quantum mechanics, it's very different. We can't just simply get a number. You can only get a probability that this could be the solution. Okay, and we'll see what that means. This is a little bit abstract right now, but it will become much more clear when you actually look at the math. But keep that in mind. Okay, so essentially that's what's saying here. In quantum physics, each observable quantity is defined by a probability. This represents the expected value of the observable, or the expectation. So when you calculate something, it is only an expected value. Doesn't mean that's exactly what you will see. Okay, and it'll become more clear later on. This is the underlying basis of the Heisenberg's uncertainty principle. So essentially, you can state the Heisenberg's principle as follows. Okay? If one measures, with a very specific case here, if one measures the position and momentum of a particle, such as electron, the best possible measurement would be limited according to delta P, which is the uncertainty in your measurement of the momentum, multiplied by delta X, which is the uncertainty in your measurement of your position, has to be greater than or equal to half h bar. Okay? Which means that if you try to find the velocity or the momentum of the electron, which of course also determines the energy, very, 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 very precisely, delta X, by definition, cannot be known very precisely. So you don't know where the electron is. If you find its energy, you don't know where it is. If you try to find the electron, you don't know its energy. And that's a very fundamental nature of reality. It has nothing to do with the theory, nothing to do with the math. It's just the way reality is. Okay, and we will see a very particular example in that little video, which I'll show you at the end of the slide. The other example is energy. Okay, similarly, the uncertainty in the measurement of energy of a particle is related to the uncertainty in the time instant at which the measurement was made. So if you are trying to measure the energy of a particle and the time it took to actually do that measurement, there is an uncertainty relationship. So delta E times delta T must be greater than or equal to h bar over 2 as well. Okay, these are very little bit abstract. So let's look at a very specific example which shows very clear. Yes?
Sorry, what's h bar again?
H over 2 pi. H is the Planck's constant. And Planck's constant is about 6.63 times 10 raised to minus 34. joule seconds. It's a very small number. So clearly, this is not important in the macro world, right? If you have a plane traveling at some speed, you know very accurately because this is a very small number. The uncertainty is already very small. It's only important at the atomic scale, where everything is small. Mass velocity, everything is small. Okay? Don't worry too much if you don't really appreciate it because it's a very difficult concept. It takes a long time. But I would say, for our purposes, you just need to understand how to do the math. Okay? But let's look at this example.
Indeed, is very, very non-intuitive. Frankly speaking, I call it bizarre.
He's one of the
but you can see it at work.
Teachers of this.
Suppose I have a laser beam here. And I use laser beam because that's right, but I could use any other light for that matter. And I make here an opening, a slit, a vertical slit.
So similar to what we saw before. But now it's
goes the laser beam right through the slit. Light goes on, and here I project this onto this wall, screen, projection screen, and what do I see? Well, you see exactly what you predict. You see here this laser spot from this beam. But now, I'm going to make this vertical slit narrower and narrower and narrower. What now are you going to see? Well, you're going to see exactly what you predict. You're going to cut off the edges of the circle, and the spot gets narrower and narrower and narrower. But
he's trying to localize
now
the
you come to
position
the
of the
point
photon now.
that this narrow slit, say, is only 1/100th of an inch wide. And now Heisenberg's principle comes in. Because now you know so precisely in the horizontal direction where the light is, that as it emerges from this slit, the direction of the light is no longer determined, according to Heisenberg's principle. And so now what you're going to see, it's going to spread out in the horizontal plane, and therefore what you're going to see on this projection screen is going to get wider. Extremely non-intuitive. Because what am I doing? I'm making the slit narrower and narrower and narrower and narrower. And what do you see ultimately? That the beam horizontally becomes wider and wider and wider and wider and wider and wider and wider. Now that is very non-intuitive, but it's the way the world works.
Yeah, so there you see it is an example of the uncertainty principle because remember position and momentum are the two variables of interest, right? Which we talked about, which are limited by the uncertainty principle. In the example, position was localized by using a smaller and smaller slit. And what the uncertainty in the momentum has to increase. Now, momentum in that particular experiment is also the direction of the light, which is not intuitive to you if you haven't learned Fourier optics, but you might know this, but I'm just making that clear. So it's consistent with what we saw before. You're trying to understand the position of the photon very precisely, but you don't know its momentum. Okay, you have to give up one versus the other. So that's a very simple macroscopic example, I guess. But in the real world, it's it really affects things like currents in semiconductors and so on, especially now that we are at a very, very small scale. Okay, now at this time, Bohr's model was based on some postulates. So obviously, most physicists don't like this. We have to make some assumptions to explain what happened. Where do those assumptions come from? So this required quite a bit of rethink of physics in terms of understanding and creating this whole idea of quantum mechanics. Okay, there were two different approaches that were developed at this time in 1910, 1915 or so. One by Schrodinger, which is basically solving a wave equation, and the other by, I forget the name, but in any case, which was based on matrix mechanics. Okay, they're basically the same, but using completely different mathematics. The wave equations are much easier to handle because they're differential equations as opposed to large matrices, which require some understanding of linear algebra, okay, which we won't go into. So let's look at the Schrodinger wave equation, which you have heard of, but we'll actually try to solve it for the hydrogen today. Okay? So the first assumption is that every particle is described by what's called a wave function. Okay? Remember, a particle is a wave, so it's fairly natural to assume that you can define a wave function to describe a particle. Okay? that wave function, psi, is a function of position and time. Okay? The probability, so what does that wave function mean? Okay? It is essentially, you can define it, for instance, as follows. The probability of finding the particle in between x equals a and x equals b is now given by this integral, where you take the absolute value of the wave function squared and integrate for x between a and b. So that's one definition of the wave function. Okay? So if you think about it, the wave function is a probability density function. It tells you, as a function of space and time, the location of the particle or at the particular instant of time. Okay? It's a probability distribution, right? Because we cannot localize the position and time independently. Of course, since the particle has to exist somewhere in space, if it exists, then this normalization condition is true, which means if you do an integral from minus infinity to infinity, that has to be 1. The probability is 1 that the particle actually exists somewhere in space. Okay? And this is called the normalization condition, and we'll use this to actually solve some problems. Okay, so far it's basic common sense. Okay? Okay, what does that mean? The physical model is something like this. If you have a wave, if you have a particle which is bouncing back and forth between, say, two walls, then it can be represented by a standing wave as shown here. Okay, if you have an electron between two walls, the probability of finding the electron is highest in the center and lowest at the ends in this particular case. And we'll actually solve this problem. Okay, or you can have something like this, where the wave looks like that. If that's the wave function, the probability is highest there, highest here, lowest here. You will never find the particle when it's at 0. So that's a physical visualization of the wave function. Okay? All right. Now, with those basic ideas in mind, let's formulate the Schrodinger equation. The Schrodinger wave equation essentially is an energy conservation equation. It's trying to calculate the total energy of a system or a particle in a particular environment. Okay? So the total energy is given by the kinetic energy plus the potential energy, as we did earlier. And it is related to the time change of the wave function. Okay? And I won't explain where that comes from because it involves much more math. Okay? So this particular expression can be written in using the wave mechanics model as follows. I h bar, the partial derivative of the wave function with respect to time. Now the wave function is a function of space in 3 dimensions, r, and time, is equal to minus h bar squared over 2m times del squared, which is just the space derivative to the second order of the wave function, which is nothing but the kinetic energy. This comes from classical physics, by the way. Okay? Remember, the second derivative of the wave function essentially gives you this is equal to half mv squared, right, which is the kinetic energy of a classical particle. Okay? And this is the potential energy. In wave mechanics, it just becomes a potential multiplied by the wave function. Okay, we'll come back to some of the formulations of these operators later on. Okay, so this, I'm just going to put this out there without explaining where this comes from. Now, if you go back here, you see the wave function is a function of both space and time. And this is a fairly complicated equation to solve because it's a partial differential equation, it's nonlinear, and you have both variables and all. You cannot separate these equations very well. So we can make a very straightforward assumption to solve these problems by hand, to get some intuition. So we can separate the time and space variables. This is possible in only certain situations. And we can write the wave function in this case as some space-dependent portion multiplied by a time-dependent portion. Okay? Now if you do that, this wave function, if you substitute that in, can be separated into 2 separate functions. One which only depends on space, one which only depends on time. And those can actually be solved. Okay? And that's what's done here. So you have a time-dependent part, which is just that. And all the partial derivatives go away because you only have one variable. Okay? And then you have a space-dependent part, where the time variable went away. Okay? It's exactly the same equation as before. We just separate the math. Okay? And in this case, E is the energy of the particle, which is this left-hand side of the equation. Okay? Okay, with that in mind, let's do a particular example to understand what these things mean. Okay, the math itself is just simple algebra at this stage, so it's not terribly exciting. But if you do an example, I think you'll appreciate what we are trying to do here. So I showed you that example of an electron bouncing between two walls. That's basically this. Okay? Imagine a potential well where the walls of the potential are very, very high. They're infinite, which means the electron has to bounce off it. So you imagine a plate with a very high positive voltage. Okay? So the electron is essentially trapped within these potentials. Okay, so this V of x is our environment. Okay? So V of x is defined as 0 everywhere, so there's no potential inside, except at the boundaries, it goes to infinity. At x equals 0 and L, it goes to infinity. And the size of the well is L. Okay, inside the well, if you look at the space-dependent part, that's the equation. Okay? Because V is 0. Okay, so if you go back here, it's basically that equation by setting V equals 0. Okay? Now, in between x0 and L. So this is a fairly straightforward equation to solve. It's a second-order differential equation, not partial, with boundary conditions. The boundary conditions are that the wave function must go to 0 at these two ends. Okay? And you should have solved this before, I think in your freshman classes. So a possible solution is basically a sinusoid or a cosine, right? This is a wave equation, and the solution is a trigonometric function, sine or cosine. The determination between a sine or a cosine is determined by the boundary conditions. Okay? Oops. So the solution in this case is a sine kx, where a is an unknown, k is an unknown. By k, we can plug it into the equation, and you can get k as square root 2me over h bar. If you put that in here, the sine kx, and solve this and plug it in, you can solve for k. Okay, because you will get second derivative of the sine is a sine, right? d by dx of sine is cos, minus, and then d by dx of cos is minus sine, right? Okay, go back and review your calculus. And then you get the sign here, so sines and sines cancel out, and you can get a kx out. Very simple, actually. I won't go through it. Okay, so you can solve for k, which is nothing but the frequency, right? Sine kx. That's the frequency of the wave. Okay. Then the boundary conditions imply that the wave function must go to 0 at the boundaries. Then you can also yes. So if you make the boundary condition that they should go to 0, that means sine kx when x equals 0. So sine kx when x equals 0 is what? 0, right? That's already 0. That's how you pick sine versus cosine. Now sine kx, what is this? This has to be also 0 when x equals L. Right? That's the other boundary condition. This equation will give you that answer. Okay? That should be n pi over L. Right? Sine of n pi is 0, right? Okay. In any case, you guys should do it by yourselves so you understand this. I don't have time to go through it too carefully. The energy of the particle then can be calculated by putting those equal. Right? Now you can see they're discretized. We didn't make any assumptions, right? This just gets discretized by the boundary condition. There's no postulates here. That's an important point here. This discreteness comes from just the boundary condition. Okay? Now you can make them equal and solve for the energy. And the energy becomes discretized as well. Okay? The energy is quantized, and n is now a quantum number. Then n becomes that. So in an electron or a particle trapped in a potential well has discrete energy levels, with the only assumption that the boundary conditions have to be satisfied, that the wave function has to go to 0 for the boundaries. And solving Schrodinger's equation, of course. So now you can use the theory to explain the assumptions that Bohr had to make, for instance. And that was a very big deal. I mean, it doesn't sound like a very big deal now, but it was at that time. Okay. Of course, we also need to calculate the A, but that's straightforward. We know how to calculate the A because we have the normalization condition. The particle has to exist in the box. So if you integrate all the way from minus infinity to infinity of the absolute value squared of the particle, of the wave function, okay, that should be 1. We know that because the particle has to be inside the box. It cannot escape the box because the walls are infinite. Okay, and you get an expression such as that, and you get A equals square root 2 over F. Okay, pretty straightforward. And you plug that in, and you get a solution for the wave function. Looks like that. What does it look like? These are the solutions for the different values of n. So this is the potential. Okay, 2 potentials. What does the wave function of the electron look like? At n equals 1, it looks like that. The highest probability of finding it is in the center. At n equals 2, it looks like that. Oh, sorry, it looks like the blue curve. The lowest probability of finding it is at the center and at the edges. Okay? N equals 3, it looks like that. And this is reality. This is the way electron would behave. Okay. Remember, this is a probability. If you square it, it's as shown here. In this case, we took this blue curve and squared it and plotted it. It looks like that because the negative value is squared up, right? So this becomes up. And that can be thought of as a probability density function. Remember, the integral of the square over some space we are interested in looking at is the probability that you will find the electron in that location. Okay? So in this particular case, there's a high probability you'll find the electron here or here, and there's a very low probability you'll find the electron here, here, or here. Okay. Now, recall the video that you saw, the cartoon before. If you open up this box to look at it, to see where the electron is, it will be at a particular location. It's not going to be at all these locations. Okay? And that turned out to be a huge philosophical problem in quantum mechanics. How do you explain that? The observation changing reality. Okay, and it's still not, I would say, not fully appreciated. And you might have heard of the Schrodinger's cat problem. You put a cat in a box with a radioactive element with a certain half-life. The radioactive element has a probability that it can emit some radiation and kill the cat. But there's a probability it may not. So while the cat's inside the box, we don't know if it's dead or alive. In quantum theory, it's in a superposition of both dead and alive states. So when you open it up, of course, it's dead or alive, which means the current understanding of reality is that the wave function of the cat, if I can draw the analogy here, is a superposition of, let's say, the alive state, which may look like that, and the dead state, which might look like that. So it's a sum of these two states. But when you actually open it up, it collapses to one of the states, dead or alive. Okay. It's a little bit tricky, but and I don't expect you to understand because I think most physicists don't really understand it themselves. Yeah, that's one way to think about it. But it turns out one can actually observe particles more recently, experimentally, without altering the boundary conditions as well. So it can be done, and people have done it, and it still collapses. And yeah, it turns out to be very technical explanations to these things. But that's just the way it is. That's all I can say. I mean, my understanding, as far as I know. Okay, now we have to make a few other technical comments here. Calculating observables. Okay, so in quantum mechanics, as opposed to classical mechanics, calculating something is very straightforward. You solve an equation, you have a variable, you calculate it. Okay, In quantum mechanics, it's very different. Like I said before, there's an uncertainty in calculating observables. The observables mean mass, velocity, whatever you can observe, right? In quantum mechanics, one needs to use what's called an operator. The wave function determines all the observables. But in order to calculate the observable, you need to operate the wave function with something. And this is called an operator. Okay? So the definition is the following. The expectation of an observable, which means that the expected value of an observable can be calculated, and it is written like that with these triangular brackets. That's a formalism determined by Schrodinger, where you do an integral of the complex conjugate of the wave function multiplied by the operator of the observable, as we'll see in a second, multiplied by the the wave function itself. Okay? And this, in Schrodinger's notation, is also written like that. Okay, you might have heard of this called the Bra notation. Okay, it's the same thing. This is equal to the observable value, expected value. Okay? Of course, it's very different than classical mechanics. So, before we do that, so let's look at some of the observables here, and we'll do an example problem. So every classical variable here has an observable representation. For position, it's just the same. It's just x. For the potential energy, it's just the potential as we saw in the Schrodinger equation. For some function f, it's just the function f, and that's not important right now. For momentum, let's say px is that, so it's different, and that's important, as we'll do an example of that. So it's h over I being the square root of -1 times the derivative with respect to the space variable. Kinetic energy, of course, is p squared over 2m in classical mechanics. In quantum mechanics, it's that. You can, of course, derive it from there. And if you have a function which is a function of momentum, then you have to do it the same way. It's a function of the operator. Okay. These things will become more clear when you actually do some examples, but you should be aware of this. Again, you don't need to memorize. You can look it up. Total energy is important because we will be calculating energies. It's just that. That's just the right-hand side of the Schrodinger equation. Right? We already saw that. And that on the left-hand side is the time version, which is this. Okay. Now let's do a particular example. So given, it's not very easy to see. Actually, I want you guys to do it. I'll go back and show you what the momentum operator is in a second. So you don't need to memorize it. So given a wave function of a plane wave. So imagine a wave of light. Okay. This plane wave, for instance, light from the sun. Okay, there's a wave function given by a e raised to j kxx. Okay, j square root of -1. Right? That's our notation. Kxx. Okay. Now, what is the expectation value of the x component of its momentum? So, px. Let's go back and see what the momentum operator is. It is h over I. Forget, is it h or h bar? It's h bar. Can you see? I don't know if it's too low.
H bar.
I think it's h bar. I actually forget. It looks like h bar to me. It doesn't matter for now. We'll look it up. Okay, now why don't you discuss with your neighbors and try to solve this problem, example problem. I have the solution here. So, I mean, not here, but I have the approach to it. Okay, so that's the definition, right? What we just talked about, the operator. No? We have the wave function, we have the operator, and then we have the wave function again. This is a complex conjugate, right? Okay, that's just the definition of how we calculate observables in quantum mechanics. So let's just do this very quickly. What is the complex conjugate of this? Someone tell me. Yes. Is that right? You guys know what complex conjugates mean. Okay. And this is around. No? See, straightforward, right? Oh yeah, J. Sorry, they are the same. Yeah, I messed that up. Some people use I, some people use so. Okay, now this is easy, right? What's a partial? Of course, we don't need to do partial derivatives, right? There's only x. We can replace this with just a regular derivative. What is that? Someone? Yeah. Yeah, derivative and exponential is exponential itself, right?
I don't know what x you're even going to take a derivative of to get that.
Of this side, remember, this is an operator that operates on this side. Operator operating on this side.
Okay.
What else can you take a derivative? Nothing else.
That's why I'm so confused.
But it's an operator operating on the wave function. That's a way to think about it.
That's just going to operate on my a to the ej.
Yes, that's your wave function. Yeah?
Okay.
You can take the derivative. Pretty straightforward, no?
I could take the derivative of that.
Yes. This has come down. So what is that? Let's write that quickly. Is e to minus 3kx x h bar I. So what was the answer? A j kx e raised to. Right? Okay. Pretty easy, right? Oops, this should be j. So these things go away. These things go away. So you end up with a squared h bar kx and that. No? Pretty easy. Oh no, till here it's easy. I agree. No? Okay, well what's the problem now? Till here. You can't read that? Oh, I'm sorry. Okay. You'll have to do it yourself, I'd say. And if you have trouble, just come and ask. Or you can come over here and look at it after the class. We're almost done.
I think the math part is understanding where it came from still.
Yes, I agree. Understanding where it comes from is not easy, and it'll take some time. So don't give up. Just read and do some examples. Of course, this is an engineering class, so we don't need to really understand the details of quantum mechanics. We need to understand enough to be able to solve problems and understand what's coming next. So, it's okay. You don't need to be an expert at this. So, of course, there is one more complication before we finish up. That this integral is not defined, right? That's infinite. Okay? So that requires some special care in how you handle it. This is handled with what's called the normalization. Okay? You have to actually divide this, as shown here, by the total value. Okay? This comes from the normalization condition. Right? Because we don't know what A is. Okay? And you apply what's called the L'Hopital's rule from calculus. Apply limits. Yeah. That's right, yeah. So you can do that yourself. And the answer becomes h bar kx. And this is very interesting, because remember what we started off, it was a plane wave whose frequency is kx. What we are trying to calculate was px, and we calculated this as h bar kx. This is the same as the de Broglie wave equation. Momentum of the photon is h bar 2 pi over lambda. Sorry. H pi over lambda, which is nothing but the matter-wave duality equation. So it's a plane wave sending a photon as a momentum given by that. Okay? One more concept that we need to cover, and those of you who can't see it, you're welcome to come over here and look at it in 5 minutes. Okay? The last concept to understand is quantum mechanical tunneling, and this turns out to be important because there are some devices that we will study which use this. So remember, in the potential well problem, we assumed that the potentials were infinite. In reality, no potential is infinite, first of all, in atoms and crystals and so on. There are potential barriers, but they are finite. Okay? When they are finite, then there is a finite probability that the particle can penetrate the barrier. And this turns out to be quite important for many, many applications. And this idea of penetrating a barrier is called quantum mechanical tunneling. Okay? The idea is shown here. It's a purely quantum effect, so you cannot explain this from a classical perspective, and we actually use this today. Okay, many, many devices. So this is the potential barrier, which has a finite potential of V naught, and the potential is finite. The wave function, instead of going to 0, of course it's 0 here because infinite, this potential is still infinite. Here, it actually penetrates into the barrier because the boundary condition the wave function must be continuous across the boundary, and the boundary condition here states that it should not be 0, which means it needs to go through, which also means that if the barrier is thin enough, some of the wave function can actually leak across, which means that you can have a situation where the probability of finding a particle outside the barrier is greater than 0. Okay? And this is referred to as tunneling. And from a particle perspective, the particle picture, the electron in here can tunnel through. There's a small probability that the electron can tunnel through this barrier. The larger the barrier, the lower the probability of tunneling through. Smaller the barrier, higher the probability that it cannot tunnel through. We'll come back to this when we talk about some devices called resonant tunneling diodes later on. Okay, we're going to stop here. Okay, let me write down the review problems, which we will go through tomorrow from the text. And you're welcome to go through it yourself. I mean, if you don't want to come to the review session, that's fine. So just do them yourself. Let's see. So 1.1 from the text. 1.5, 1.6, 1.12, 1.14. That's from chapter 1. And if you don't have the book, just come tomorrow.
So is this homework or is this just review problems?
Just review, just for your practice. You don't need to come. But I would encourage you to come because, like I said before, a lot of this is very, abstract, and in my experience, you have to actually do some examples. Yes.
When will we be getting the first homework assignment?
Tuesday.
Tuesday.
Yeah, and you'll have 2 weeks to do it.
Perfect. Thank you.
2.6. That's it. Okay.
I had another question.
Yes.
Will you be doing a similar presentation that you'll post online from the review section as well?
Sorry, say that again?
Well, like you're posting the presentations you're doing here in class.
Yes.